think we've given everyone enough grace. So just quickly before we start, welcome everyone to, and thanks for coming to this second in our climate change seminar series. Today's speaker is Professor Christian Jakob. Before he joined Monash University, he worked at a number of meteorological organisations, including our very own Bureau of Meteorology here, the European Centre for Medium Range Weather Forecasts, and the United States Department of Energy. Christian's a CI and also former director of the ARC Centre of Excellence for Climate Change Climate Extremes. As well as having an outstanding track record with well over 11,000 citations, he was also shown excellence in leadership. He was awarded the 2017 Morton Medal from the Australian Meteorological and Oceanographic Society, recognising his leadership in the field and also mentoring of students. A major focus of his research is improving the representation of clouds in climate models. So without any further ado, I'll hand over to Christian. There'll be time for some questions at the end, and then we'll finish up as last time with some posters. So thank you very much, Christian, for agreeing to give this talk.
Yeah, thanks, Pam. So when I prepared this talk, I found it very challenging because I want to talk about climate models. I'll put up the title in a second. And there's mathematicians, there's people from physics, chemistry, there's users of climate models in several of our schools. There's people who know a lot about climate models, people who know almost nothing about them, but use them perhaps for their research. So covering this very broad sort of spectrum of expertise that our faculty represents is a huge challenge. So I've tried my best. I think the people who work in weather and climate will probably get the least out of it, but they may have a bit of fun every now and then. I'll try and make it as entertaining as I make it scientific as well. So let me share my screen so you see my talk. Here we go. Hopefully everybody can see those slides. So I'm going to talk about climate models. I'm going to tell you what's great about them. I'm going to tell you what's not so great about them. And there's absolutely nothing that's ugly in climate models. You can trust me there. So I want to take on in the end what the future of climate modeling might hold. And it's actually a pretty exciting time for climate modeling. So let me tell you a little bit about what they are, how they work. Actually, I find whenever I give presentations about climate models to people who use them, very few actually know what's inside the box. And so I am going to spend the first part of this talk to open the box a little for all of you, including those of you who don't like math and those of you who love math. So we'll do this in a very sort of mixed way. And then we'll talk a little bit about, given what's inside the box, what can we actually do with them? What are they really, really good at? What might they not be so good at? And how can we make what they're not so good at better? So the first question you may have, I always have, is why do you want models anyway? What's the point of having models? Okay, and what in my world, what's the point of having climate models? So here's a curve, and I deliberately deleted the rest of it, of the observed global mean temperature. This happens to be a model reproduction of these observations. Doesn't really matter, but we want models not only to make predictions. In weather and climate, we think of the purpose of our models first and foremost as being one of prediction, but that's not true really. Models are tools to understand stuff. So we see this curve, and one question we may have is, why does it look like this, right? What makes it look? What makes the bumps? We can see there's these cold bits here. There's little bumps where it gets cold. Where do those come from? And it seems to have this overall warming between 1950 and the 2000s. Where's that come from? Have humans have anything to do? Have we shaped this curve in any way, shape, or form? But then, of course, we also want to know what happens next. And when I thought about what happens next, when I give this talk, I often show things that are completely unscientific. And as I was digging for unscientific things, and I don't know whether he's here today, I discovered Peter Kaywood's secret lockdown hobby. Peter, if you're here, I discovered your secret lockdown hobby. And that is gazing into crystal balls. If that's not Peter Kaywood, I don't know who it is, right? So there you are. So of course, in science, we don't use crystal balls, we use models. And so everybody thinks they know what a model is and consequently everybody thinks they know what a climate model is. But what do we actually mean by model? Well, it turns out there's sort of several classes. There's statistical models, and I found one. I actually want to use it and see what it does. I just found one digging around that Facebook is publishing called Profit. Of course, what else would it be called, right? And it claims that you can give it any time series and it will make a prediction for the future from that time series. And then it's in the fine print, it says, if the time series has oscillatory behavior, it works best. Well, hallelujah. We can predict the sine curve. Well, how good is that? Anyway, here's their prediction of that continuation of that blue curve from the statistical model. But the point is, the model is entirely built on data. You train it, and then you use it to extrapolate it to the future. Most models we encounter in society are more advanced than that. Some are statistical, but a lot of the ones that we encounter are, of course, based on what our friends in mathematics call differential equations. And these the ones that have predictive power in time would have a derivative with respect to time. And I dug up, this is a COVID model. Okay, you can find it in Gumel et al. In a journal called Infectious Disease Modeling. And the whole point of it is a bunch of variables, and the dot means it's the derivative in time. And you can see these are all linear equations. There are lots of parameters and they're coupled to each other. Okay, so you can calculate the behavior of COVID with that one. Great. So differential equations is a sort of standard thing, but most of them are made up, actually. But so are climate models statistical models? Are they different? Do they have differential equations or what? So they are models based on differential equations, but with a very, very, very important distinction. And that is the differential equations we use are the basic laws of physics. Okay, so it's not made up differential equations like in an economic model, a model that predicts the exchange rate, or in the COVID model that we just saw. These are sensible setups for these differential equations, and then there's lots of parameters to estimate. But we start from very simple first principles. So I put two here, Newton's second law, which everybody knows from high school, and obviously you know it from your work probably, F equals ma, and that allows us to calculate three-dimensional wind vector, the three-dimensional movement of an air parcel. We follow an air parcel around if we know the forces that act on it. And we can do that. And I'll show you in a second what it looks like for an atmospheric model. Another very famous one is the law of energy conservation expressed in the first law of thermodynamics. And with a little bit of very few assumptions, we can rewrite that. And we can say that if we heat an air parcel, or heat or cool an air parcel, it changes its temperature and it changes its pressure. And it turns out, and you can see both of these have the little d by dt, so it's a time dependence. So that allows us to look into the future potentially with these models. Okay, so it's that simple. And it's really important to realize that when you look at the big class of climate models most of you use, which are called general circulation models, they all start with that. Here's an example if you go further with this and then apply these equations to the atmosphere on a sphere, you get equations that look like this, and the details really don't matter. The key to realize is that they are all that there's nonlinear terms in here. They are coupled, so there's a v in the u equation and a u in the v equation, and so on and so forth. The nonlinearity comes because we can write these total derivatives as partial derivatives, because all our variables are dependent on space and time, so they have 4 coordinates. So they become partial differential equations to this. They're nonlinear and they're coupled. Well, bottom line, no one can solve those on a piece of paper. So to solve this and to actually apply these equations to the problem of climate, and these are just the ones for the atmosphere, we'll come back to that, we have to put them on the computer and we have to solve them numerically. Okay, and this is where it gets interesting, because to do that, we have to make approximations, right? So we start with an equation set that's actually the laws of physics. So that sounds great, because it should allow us to make really good predictions. But now we need to put them on the computer. And that gets interesting, And I don't remember who of you watched Little Britain. That might be well before the time of the youngsters, but the older people may remember this comedy series. So we can only solve them numerically, and we make approximation. The first approximation, perhaps the most important one we have to make, is we have to divide the Earth into boxes in 3 dimensions, right? So these become little cubes or something. Think of them as little cubes. For the atmosphere, upwards; for the ocean, downwards into the ocean; for the land, into the land, because we want to go down into the soil at least for a few meters, because heat and water get stored lower down in the soil. So we have to make these boxes, and as every numerical mathematician knows, the answer is better the smaller you make the boxes, right? So you get a better answer from your numerical implementations if you can make the boxes small and the time steps that you move forward short. But the computer says no. You remember the travel agent in Little Britain, always sitting there typing, and nah, computer says no. And we have exactly that problem in climate modeling. Even with the best supercomputers on Earth, there are limitations on what we can do. And remember, modeling the climate, and we'll come back to that too, means to model at least a few decades, right? In a weather forecast, we make a prediction for the next week or so, but to think about climate, we need to model decades. Turns out for climate, we can't just model the atmosphere. Other things matter too, like the ocean, ice. We might even want to model the last glacial maximum. Now we're talking thousands of years or hundreds of thousands of years. So depending on what it is we are interested in the climate, we have severe limitations coming from computing. So the first approximation is the boxes need to be relatively big. On the left here, you see the Earth. If we made the boxes 2.5 by 2.5 degrees, 250 by 250 kilometers, ridiculous, I hear you shout. But that's what climate models looked like about 5 to 7 years ago. Today's global climate models are more in this 1 by 1 degree range up here. But I like the 2.5 by 2.5 because, is there anybody in the audience from Tasmania? Why am I asking this? Bad luck. Climate predictions for Tasmania with this model, you out of luck, you don't even exist. Even if you do exist, like New Zealand, you don't exist very well. You get a couple of boxes, right? And we know New Zealand has massive topography. The weather on one side of that topography is very different, and the climate on one side is very different from the other. And really, these models have no capability of representing the topography and orography really, really, really well. So that's an issue. At 1 degree, of course, things get better, but here's Europe or parts of Europe, Spain in the middle at 1 degree, and down here it's at 15 kilometers. And you can tell the difference in the Pyrenees, can't you? And the Alps don't look that terribly realistic at 1 degree. And the reason I'm mentioning that is there are consequences to that. I mean, the big consequences if your island doesn't even exist. So making a climate prediction for Tasmania with no Tasmania in the model is kind of hard. That's an extreme case, but we have to recognize that we have now approximated the Earth. It's no longer the real Earth, because we had to make these grid boxes. So that's approximation number 1. It leads to the wrong topography, the wrong orography. All these things matter to the weather and to the climate. So we expect that there must be consequences from this, and that our models can't be perfect representations of the real climate. There will be limitations to what we can do with them. And that's the important bit. Gets slightly worse. So once you've decided to make a box of 100 by 100 kilometers, 1 by 1 degree, there's stuff inside that box that's smaller. And if that stuff doesn't matter for how the climate behaves, then you're good. But once we made a 100 by 100 kilometer box, all we know is all these variables that our equations represent. We only know the averages, okay, over these boxes. We don't know the distribution of those variables within our box anymore. We only know the averages. Now that's a problem for things like these wonderful thunderstorm clouds here. So this yellow bit is our grid box, and within that you can see there's a whole range of clouds. These are convective clouds. They go relatively deep up into the atmosphere. Condensation happens in them that heats the atmosphere, the rain falls, it evaporates, it cools the atmosphere, that leads to changes in the circulation. So not having these clouds represented is not an option, because they are massively important to how the climate system behaves, how weather and climate behave. So we need to re-engineer them back into the models, and we do that by a process called parametrization, and that's simply making an approximate little model in the big model, right? So it's the sort of stuff I used to spend my career on, mostly, no longer. But that's where I had most of my fun when I was younger in my career, right? So we have to build these parameterizations, and they are approximations. There's another form of approximation. No reason to go into more detail. There's a whole bunch of equations that we use to write these parameterizations, but these are much more like the differential equations of the COVID model. So we have some idea how the system works. We express that in a bunch of equations, and we have parameters that we have to estimate somehow from observations or something else. So we have another level of uncertainty.
Tutto a posto, che fai di bello? Stai facendo la
Finally, Fabio.
Senti, che faccio? Ti vengo a prendere io, ti accompagni la mamma?
Sì, that's all I know in Italian. Hey, all right. So we have the next question then is, if you simulate the climate, what do you need to include, right? So it gets even more complex, because we can't just get away with just modeling the atmosphere, which turned out to be complicated enough, and turns out to be the bit I know the most about. So the blue bits here is what's traditionally has to be included to think about the physical climate system as a minimum. It's the atmosphere and its circulation and radiation going through it. It's the ocean coupled to the atmosphere and its circulation. So we have a three-dimensional model of the ocean that goes to great depth, and we need to know not just the surface circulation, but also the deep ocean circulation. The ice that floats on the ocean is, as a minimum, needs to be included. The ice that sits on land, like Greenland and Antarctica, we'll come back to in a second, we often treat as stationary for shorter term climate problems, but it turns out that's no longer an option either, because it's changing dramatically as the climate's changing. And we need to include the land physics as a minimum, the physics and the hydrology. The green bits are the bits that are also important, and depending on how long into the future we want to look and how interactive we want our system to be, also how long we want to look in the past, we may want to include those as well. So we may have to include some chemistry, especially to make little air particles in the air called aerosols, on which clouds form. We may want to introduce vegetation, because if you simulate the climate and if it changes a lot, the vegetation will change, and that will have a feedback on the climate. Now you write down the equation for a tree, I give you a prize, right? So the vegetation becomes one of those uncertain models with lots of parameters. We have basic ideas of how vegetation responds to temperature and rainfall and so on, but there is no fundamental law like Newton's second law that we can go back to model vegetation to the detail that you could imagine. Same is true for plants in the ocean, right? So the ocean ecology and biogeochemistry. So those need to be included, and I've already talked about continental ice sheets, and it all depends on what the purpose of your simulation is. How long do you want to go back or forwards in time? Which of those is important and which of those is, right? But it's a complex beast that we are building. Oh, one digression very quickly. The question I get asked very often is, well, this climate modeling is all quite hokey. You can't predict the weather for more than a week or two. How can you say anything about climate, 50 years from now, 100 years from now, 2000 years ago? It's just hokey. And I just want to sort of clarify where that difference coming from. And it's actually quite important for understanding some of the things we do with climate models. So for weather, we are talking about the weather problem is an initial condition problem. So we need, if we take this set of equations here they are again for the atmosphere. And if we know the state for all these variables at the beginning of our prediction, we can integrate them forward in time and figure out how the weather is going to change. So the key ingredient to weather prediction, and the reason it goes wrong most often, is that we need to know the initial state of the atmosphere in every one of our boxes for every variable. And of course, we don't have observations to support that. So we use a technique called data assimilation, where we optimally blend what we can observe with satellites, aircraft, stations, balloons, ships, and so on and so forth, radars. We take all that and combine it with a prediction that our model made to get an optimally blended product that we use to start our forecast. And if the forecast is right or wrong, really critically depends on whether we get this initial state right or not. Especially if we get it wrong in a place where the nonlinearities of the problem matter today, then we can get a very bad forecast at times. Now, the climate problem is completely different, has really very little to do with the initial conditions. The system forgets about the initial conditions within a month. For the ocean, it keeps its memory a bit longer, which is why we can make predictions for El Nino and La Nina events, seasonal sort of predictions a few months ahead. That memory for that comes from the ocean. But for the climate, really, we're thinking of a boundary value problem. And if you write our first law of thermodynamics again, it's all in this heating term here. In one of the components that heats the climate system is driven by radiation from the sun, and then the Earth emits radiation, and radiation is transmitted through the atmosphere. And if the climate's stable, what comes in goes out. They are the same. But when the climate's not stable, like right now, there's an imbalance between the incoming and the outgoing radiation. So this radiation is very strongly driven by the composition of the atmosphere. What happens to the radiation as it gets transmitted to through the atmosphere, both at wavelengths from the sun and at wavelengths emitted by the Earth. And so if we know the composition of the atmosphere, and if we can tell the model what that composition is like, then it can simulate the evolution of a climate system. And here the goal is no longer to precisely predict the 1st of January 2024, but the idea is, what would a typical 2024, 2035, 2050, what would a sample, a possible 2050 look like? That's sort of what we're trying to do. And so here's just this composition of the atmosphere. This is the famous Keeling curve, increase in carbon dioxide, pretty up to date, 16th of September. We are well above 410 parts per million. And this is the temperature evolution from the 1880s to 2021 is the one with the dots here from the data set put together by NASA. And so we see this increase in CO2 and we see an increase in temperature. And you all know that's not a coincidence. Okay, so the beautiful thing is we put all this together. We take all these equations, these submodels, oceans, atmospheres, land, and we put them together, and something magical happens. In a sense that the behavior of the Earth that is observed is actually emerging from those models. And we can use the data sets, the observations we have about the Earth. We really haven't used them all that much to build the models, right? The models were built on basic equations, made approximations. There's a little bit of data going in to design those parameterizations and estimate parameters in them. But other than that, it's not like the rainfall or the air temperature have gone in. And yet, when we ask the model to simulate the Earth, we get sensible answers. We always take that for granted, but it's actually quite a remarkable thing that we can do that, right? You take a bunch of equations, you approximate them, you stick them on a computer, and out comes something that you can actually observe. That's pretty good. So here are some climate model results. This is the near surface temperature. This is the rainfall. These are just long-term averages, and they actually look like observed rainfall. We will come back to that. This is the evolution of the temperature since 1850. This is globally averaged. Each of these squiggly lines is a model. The black line is the observation. The red line is the average over all the models. And you should be quite impressed how close they are to each other, actually. There are issues. So these little lines tell you what the global mean temperature is that each of those models actually predicts. And you see there's actually, even in the global average temperature, models differ from each other. So we can see that there's really good stuff happening. But we can already see from this plot, not all is perfect. We get quite a range of global mean temperatures in these climate models. Despite the approximations we've made, we can learn an awful lot from these models. And the two things perhaps that are most prominent and came back out prominently in the recently released report by the IPCC is that humans affect the climate, have affected the climate in a major way. And we can also learn what the future might hold depending on how we behave as a species. So the first one is in this picture. You can only do this with a model because the real Earth has already done what it's done. So we take the models and we give them the atmospheric composition as we've observed it, including all the human influence, as there's human influence and natural influences. These dips, by the way, are natural influences. They're volcanoes, major volcanoes, which tend to cool the Earth system. And we tell the model that there was a volcano, so the model knows about this from observations. But it also knows that carbon dioxide has increased, for instance. And then it simulates, the models simulate this brown line, and the spread is these different models that you saw in the previous graph. But because it's a model, we can also pretend carbon dioxide never increased. And aerosol particles that we put in the air, that never happened. We were never here. We never did that. It wasn't us. So what would happen to the climate then? And that's what this blue curve shows, or this sun, whatever this color is, greenish bluish curve. And what we see is there's the two curves diverge majorly, and by today they have diverged so massively that there's no doubt in our mind that we cannot explain the observed climate, which is the black curve, without the human influence. That's a very powerful thing to do with a model, right? And you have to have models to do it. You can't deduce it simply from the real Earth. So that's a very powerful message, and we've become surer and surer and surer about it. And despite the models giving a range of answers, as indicated by this line, the separation is clear as daylight. We can also use them then to look into the future and say, so if we know, or if we make assumptions about what the composition of the atmosphere might be into the future, which is done with some scenarios, then we can estimate how the global mean temperature might behave. And again, here are a bunch of scenarios. A very optimistic scenario is this sort of sine curve, where we really try and take action and reduce our emissions pretty rapidly, pretty soon. And it goes all the way to a very pessimistic scenario where we burn, baby, burn, right? And then we say, okay, so what would the resulting global mean temperatures look like? And here's the graph on the right. This is also from the recent IPCC report. And again, the key message from this is probably that despite these approximations we had to make and the uncertainties we have in our models, the number one uncertainty what our future looks like is human behavior. It's which of those paths are we going to choose? It's not how good are the models. For global mean temperature, it's clear that our behavior will drive a very different future for ourselves. And again, we have climate models to thank for our ability to say that. But not when's the last time, so this was all global mean temperature, right? So when's the last time you planned a barbecue based on a forecast of global mean temperature? Not really, I don't think. I don't think any of us have done that. So what's really important for many of the things we are interested in with climate change is what happens in our neck of the woods or what happens locally somewhere else in the world. So then the question arises, how good are these models in representing that? And that's where the limitations become more severe. So this is from a paper, quite old paper in 2011, where the authors looked at how does the error just in the climatology of temperature on the left and rainfall change with the scale over which I average. Many of the figures I've shown you, we've averaged over the whole globe. So here they take the average over length scales of about 10,000 kilometers all the way to the actual individual grid size, which in those days would have been about 250 kilometers at a site, right? And the only message to take away from this is the errors get larger as the scales get smaller. And it's these small scales that matter to many of you who use climate models to look at, ecosystem change and other things. You are interested in local changes. Society is largely interested in local changes. And the message is that's much harder for the climate models to say something about. Here's a map. I've already showed you the one here. This is the mean rainfall coming from, or the numbers aren't on this particular plot, from a large number of climate models, order 50, averaged together. This is their mean error. So this is the rainfall itself, and this is a comparison to observations. And what we see is that these errors can be, 30% or something like that. So you see this green bit is 3 millimeters a day in a region where it rains about 9 or 10 or even less. So these errors are actually still quite large. So what's globally average, you're good. Once we look at individual regions, we can identify pretty large errors in the models. And some of these errors are as large as the signal that we're trying to predict. Unfortunately, in the 6th assessment report, the change of rainfall is always expressed in percent, and the error is always expressed in absolutes, in millimeters per day, which are the units of rainfall meteorologists use. So it's quite tricky to compare those two, because you can see these large changes, 50%, but they seem to be where it doesn't rain very much. And then the changes on either side are smaller, they're only 10%, but that's where it actually rains a lot. So the signal that we're getting, how much is the rainfall going to change as predicted by these models, can be of similar magnitude as the errors, and that makes us less comfortable in being really out there and saying climate models are great to predict rainfall at any location. You pick a location, rainfall will be good. And I'll come back to that in a second, because it's something that's probably very hard for you to see on your screens on these maps, and that's this stippling and little stripes that you can see. And they are actually highly relevant because they tell us something, but I'll show you more in a second. Now, this scale dependence of the error also leads to a scale dependence in the uncertainty for future predictions. This is from the same paper. This time we are not looking at error because we're looking into the future, right? These blue lines are 2080. This is for temperature on the left again, rainfall on the right. This is just how different are the models from each other. What's the spread across the models? And it shows very similar behavior to the error. As we get to smaller and smaller scale features, the models get more and more different. And if we want to interpret, and it's almost okay to do that, but not entirely okay to do that, we want to interpret the spread between our models as the uncertainty. It's an estimate of the uncertainty. It's not for sure the best estimate we can make, but it's a good estimate of the uncertainty, good first stab at estimating the uncertainty. We see the smaller the scales, the larger the uncertainty. And that's important for you to keep in mind if you use climate models for anything. The smaller scale you look, the more uncertain things get. And we can look at that in map form again. And this is coming back to these change maps. So this is the change of rainfall at 2 degrees warming. This is the change in rainfall at 4 degrees warming. We see 4 degrees makes a bigger change than 2 degrees. So it's good. Things seem to scale with the amount of change, which means if we can reduce the change in temperature, we can also reduce the change in rainfall. But this time what I want to highlight is these stippled and hatched areas. And that basically says we can't really tell. The change is smaller than, it's either not robust or not large enough, or we have conflicting signals from the model, different hatching. If you look over Australia, the only region where there's no hatching is the southwest of Australia, and it's really almost offshore of the Australian coast. Everything else has this hatching, so the signals are relatively small. The model uncertainty is relatively large for rainfall in those regions. So we really are much less certain when it comes to predicting rainfall. That shouldn't surprise you, because remember, all this, the clouds are small. The clouds that make a lot of rain on Earth are smaller than 100 by 100 kilometers. And therefore they have to be introduced in the climate models by form of parameterization. And that increases the uncertainty. Okay, I'm almost done. I want to spend 2 slides on thinking about the future. And there's many, so we agree that the climate models could be better. They're great. They're giving us an enormous amount of information. They have changed the world. If you think about it, the Paris Agreement would not exist without climate models, right? I claim we would not be in in where we are, even though we might want to be even further than where we are in our action taking around climate change. We would not be there without climate models. And so they've been an absolutely revolutionary tool. They've also been a great tool for science, which I didn't talk much about today. We can learn an awful lot from just doing cool experiments with them, right? Changing, asking if and what questions with them. But they could be better. So really, society is now increasingly interested in information on these very small scales, right? So we want to know, for example, what's the tropical cyclone frequency going to be in the northern part of Australia, and where are they going to go further north, further south? What's the rainfall distribution going to look like across Australia? Are we going to get more extreme rainfall? And it's not just are we going to get more? The answer is yes, but where are we going to get more? And that's much harder to answer than the are we going to get more? The first one is a pretty resounding yes. The question is where and to what extent, and what quantitatively what will change. And that's a question that we have a hard time answering at this point in time. So the second thing that's happening is society is really not interested in rainfall. Society is interested in what rainfall does to infrastructure, flooding. It's not interested in wind, it's interested in what the wind does. Can we make energy from it, right? If we want to be carbon neutral by 2050, we need to deploy renewable energy at unprecedented scale. We better know whether the wind's changing somewhere, whether the sunshine's changing somewhere. So these are the questions that we are faced with right now. It's no longer about global mean temperature. It's about barbecues and no longer about global mean, and which we can't plan based on global mean temperature. So to do that, we really need to up our game in modeling. And one of the big trends is to try and eliminate the representation of thunderstorms by parameterization. And to do that, we have to push our model resolutions for it to happen to about 1 kilometer. Maybe 3 will be good enough, but to about 1 kilometer. We are at 100 by 100 now. We want to go to 1 by 1. That's a big deal. We also want to integrate societal models. So there's a program in the World Climate Research Program that's trying to do this. It's called Digital Earth. Some of you may have heard about the concept of digital twins, where it's sort of an engineering concept where you make a copy of the real system in a computer, hence a digital twin. And then you can play the if game. What if I change something here? How will my engine behavior change, for example, if you have a digital twin of your car or aircraft engine? And we want to do the same for the Earth. And it's a pretty ambitious project because it includes not only Earth system models at very high resolution, and we'll come to the high resolution bit on the last slide for a bit of fun, but it includes the models that simulate the impacts. It includes observations. It tries to integrate observations with models to give us the best estimate we can possibly have of what the state of the system is at any given point in time, including going back into the past and getting full 4-dimensional estimates of the state of the system, the atmosphere, the ocean, the land. And we really want to connect that to the things society cares about, which is health, the economy, how do we produce energy, what will happen to biodiversity. These are the topics that should drive this rather than what's going to happen to rainfall, because that in itself is interesting, and meteorologists, we get excited about that. But society really wants to go the next step and say, what's it mean if the rainfall is changing? And one of the exciting bits, especially for the young people in the room, to achieve this really requires us to push our connection and interaction with digital technology. From high performance computing to data, the data that these models produce goes into petabytes. You know, your little gigabytes or your 1 terabyte or 2 terabyte hard drives that you buy are laughable compared to the volumes of data. The more boxes you have on Earth, the more data you produce, right? Makes sense. And 100 by 100 going into 1 by 1 makes a huge increase in the volume of the data we have to deal with. We also want people to then be able to actually receive the output of these simulations and interact with that output in meaningful ways. So if you are an ecologist and you want to study the change of ecosystems as the climate's changing, you want to interact with that output in a meaningful way without having to know any of the details. And that's part of this digital Earth. So one aspect of this is this high resolution modeling. And I leave you with this picture right at the end. Well, actually, I leave you with a quick summary. But here's a picture of 10 models that have simulated the atmosphere only in this case, at the resolution of a few kilometers. They all vary. Some are 3, some are 5, some are 7. And then they made this picture of the Earth as you would see it from a satellite, from each of the model simulations. So 10 of these are models, and one of them is an observation from a satellite. It's actually, you can see Australia's in the middle. I was very pleased that they did that because it's mostly Europeans and Americans who put this together. But they put us right in the middle because the Himawari satellite, which is the Japanese satellite that observes our neck of the woods at high time frequency, is what they use to compare to. So have a bit of a guess, have a fun game, and then I'll resolve which of these 11 is actually the observation. And here it comes. So the point here is we are actually getting to a point in modeling where it's hard to tell the difference. If I showed you a loop and animation of this, it's getting harder and harder. With these 100 by 100, if I showed you this at 100 and 100 by kilometer resolution, you'd immediately know who is the model, right? So it's a pretty exciting time to be in climate modeling. There's a lot to be done. There's a lot that isn't right yet and we want to do better, and we know we can. So here are my take-home messages for people. So climate models are incredibly powerful tools for both science and prediction, but we have to make approximations. The approximations are often computationally driven, not scientifically driven, and there remain major issues as a result. And if we solve those problems that we have in climate models, the impact on society could be huge. So it's not just we're solving it because it's a bit of fun of scientific fun to solve, which it is, but it actually has an impact. That's one of the fun, the nice things to work in the field that we are in, is that we are not, I used to work in numerical weather forecasting, and it's kind of the same thing, that the forecasts are actually saving lives. So what you do isn't just scientifically valuable, it actually has immediate impact on people's lives. And using forgetting about building models, for those of you who use models, that's a complex problem in itself, how to do that well. And all of you who do use models for what you're doing, don't make simple assumptions. Do not make assumptions that they're great or fantastic or bad. Don't go the other way either. But actually do your due diligence and find out what you can and may or may not be able to do with them. And then investment in climate modeling, really, this revolution is underway now. And if we keep investing in it, there will be payoffs. And here's it's Christian's rule of thumb for climate model users. It's actually a coupling diagram, as systems people call it. And the larger the scale of the phenomenon you're interested in and that matters to you is, the more you can trust the model. So an arrow means there's a positive coupling, right? So the larger, the better, the more trust you can have. If you're really interested in very, very small stuff, you can trust the models less. So the smaller, the less you should put your trust into model output. Likewise, if you know your influence, the thing you're interested in is influenced by these parameterizations, your trust should reduce. So a little circle means it's negative. The larger the influence of these processes, the less you should trust the model. And so that sort of, the shorthand for this is temperature, you entrust more than rainfall. And I leave it at that, and I went over time a bit, I apologize. But yeah, getting through climate modeling 101 in 40 minutes is kind of hard. So I take any questions that people may have.
Thanks, Christian. That was a really insightful talk. I learned a lot. So as Christian said, any questions?
I might stop sharing for now so I can see people and they can see me. And then if needed, I can bring the slides back up.
All right. If no questions are forthcoming, I'll start with the chair's prerogative and ask the first question. I really like the concept of the digital twin and trying to represent more. As a biogeochemist, there's always interesting processes you can look at, and so I like the concept of representing all these ecological processes and also socioeconomic processes. I suppose there's two issues there. The first is computing power, which you alluded to, and then I wonder if the main one is non-linearities, which you kind of sort of alluded to at the start of your talk. How do you make sense of that, or how do you make the model useful within the limitations of those non-linearities when you sort of go to that scale of complexity?
So one traditional approach in meteorology, both in weather and climate, is to use more than one simulation, right? So if you have, for instance, say you have a nonlinear part of your model and it has a parameter and you don't know what that parameter is, you run the model several times and you make an ensemble of answers rather than a single answer. And then you need to exploit that, which is an art in itself. Using just the average, which is sometimes what people do, is a dangerous path. So I give you an example. Some regions of the Earth some models predict the rainfall to go up. Other models predict rainfall to go down. If you take the average, the rainfall doesn't change. Well, no model predicts that. So averages are dangerous when it comes to use, averaging nonlinear behavior is dangerous, as we all know. So the point is you do that, but that increases the computational load, of course, because instead of running one simulation, we now have to run 100 or 1,000, depending how smart we are in picking how we design these ensemble members. Integrating the full Earth system at really, really high resolution is a couple of decades away, I think. But we have to start the work now to get there. That's sort of where we are sitting with this digital Earth. The ambition is very, very large. And it's quite clear that it will take a long time to get there. But it's equally clear that we have the capacity to start now. And if we don't and wait another 10 years, then we may miss an opportunity to help society in making better decisions, actually. So yeah, it's a tricky one. So we would probably start with sub-models that are not necessarily coupled, and then we start coupling them and we learn as we go along what happens when we do that.
And I guess on that, I suppose the other key part of it is learning where the sensitivities are. As you said,
Yes.
the purpose of modeling is not to forecast necessarily. That's what most people think it is.
Not the only purpose.
But as you say, it's really about learning what you don't understand, I suppose.
Mm-hmm.
Thank you. Other questions? Just unmute yourself and jump in.
I have one, if I may.
Please do.
Yeah. Christian, great talk. Thank you very much. Sorry for the interruption. I had a phone call from touching base with my son. Anyway, it's very interesting. So you say that we need a higher resolution, and then you talk about investment from the future. Assuming that you do have that money, so if it is just a matter of high resolution, we're probably going to invest the money in computation, HPC, or do we need methods and new methods? And in that methods, which direction would you go? Would you go artificial intelligence or basic numerical method for solution to all the beautiful equations?
All of the above. So I think all of the above. There's no doubt in my mind that we can only solve this by taking this really multi-pronged approach, because we need to not only make it better, we also need to make it faster, right? So we need to get similar quality answers for cheaper. There's been there's been some work in our area to do that by, for instance, machine learning slow code. Calculating and radiative transfer through the atmosphere is painfully slow because there's so many frequencies or wavelengths to consider. But if you've done it, you can then machine learn it and run it really fast afterwards. So that there's that. You could machine learn where you don't have parameterizations, could be machine learned because there's no equations. Where there are no equations, statistical methods, as including AI, are very useful. Where there are equations, I'd stick to them just for accuracy purposes, but that's just me, and there's different opinions around the community around that. we need major improvements. HPC is a problem because it burns a lot of energy these days. Running a supercomputer, it needs its own little power station right next to it, right? So we don't want to change the climate by calculating it in a major way. So that's kind of a, so all these, then a real massive issue is the data. What do you do with the petabyte that each of those simulations will produce? And how do you make people interact with it? So there's massive challenges in all areas, and we need all methods. We standing here and saying let's not do this, it's pointless, is a mistake. I think we need lots of brains working on lots of things, and then we'll get there.
Yeah, I agree with you. Probably another problem we'll have to think about is the carbon footprint of HPC.
We do.
Yeah, thanks.
I think Cameron had his hand up.
Yeah, hi Christian, thanks for your talk.
Hey Cameron. Enjoyed
it. I had a challenging experience of dealing with a climate change skeptic who was via a family member earlier this year. And they were showing me some charts, and I believe they were probably real, that showed that climate projections of global temperature were running a little bit hotter than the observed warming. But then when I looked at the chart that you showed from the latest IPCC report, it looked largely in the middle of the spread. Is that right, that they were running a little bit hot recently? But
well, so one of the latest group of climate models has a few models in them that have a very large change of temperature for a given change in carbon dioxide. So for the in crowd, that's called climate sensitivity, right? So there's some models that have a very large climate sensitivity, and people have gone away and have looked at that, and there is now a belief that that's unrealistic. The very large values are unrealistic. There's been an assessment of what the likely climate sensitivity of the Earth's system actually is, and it's not just based on models, it's based on paleoclimate information, on process information, and on models, and building a consensus from that. So there's evidence that the very hot models are not realistic. Now, you don't see that in the plots I've shown, because in the periods where that we've observed, there's a competing effects between aerosols, which cool the Earth, and carbon dioxide, which increase in carbon dioxide and other greenhouse gases which warms it. And so they play off against each other in the observed period. But once we go into the scenarios, the aerosols are assumed to reduce. And that's when you start seeing these very hot models. So this is one of the things well known about any linear or nonlinear model. You can, in some occasions, get the right answer for the wrong reason, right? By having two compensating effects, and that sort of masks something until one of the compensating effects, in this case the aerosols, disappear from the system, and then the other one comes out. So that may be what they've seen. I don't know. It doesn't really matter, because it doesn't change anything substantial. The IPCC in some of their graphs have removed the 3 or 4 really unrealistic models. It makes no difference to the overall results. So yeah, I don't know what to say to your climate skeptic colleagues. I mean, how lucky do they feel? Ask them how lucky they feel by not taking action.
Thanks. I'll just click on the tape recorder and I'll play that back to them.
Yeah, all right. Fiona.
Yeah, I think we've got time for one more question.
Thanks, Christian. Look, I was just curious about human influence and climate models. Will the pandemic actually have any effect on your climate modeling, or is it just a blip in time? I was curious.
Well, so the pandemic will have an effect in an indirect way, right? So one of the things that's been reported is that our emissions have reduced a little because of it. That won't last, I don't think. But so when it comes to running the climate models in the future, we will see the pandemic influence as a dip in the emissions for a very short period of time. So at the moment, it's an opportunity to go on down or stabilize and go down. But we'll see how our politicians deal with the challenge. The IPCC report has been very clear that the time window is shortening and shortening to take action. Whether there is a reaction to that or not depends on the country you live in. Ours doesn't instill you with lots of optimism at this point, but there's an election sometime soon. So, you can change it. Don't vote for them. If you don't like it, if you like it, vote for them.
Thanks, Christian. I did say one more question, but is there any burning questions? It's such a privilege to have you here answering questions. If there's any burning questions, please sing out now. I don't want to cut you off.
I had one question.
Go,
Thanks,
Ning.
Christian, for a great talk. It was so interesting.
Thank you.
And I was wondering, when you are wanting to get higher and higher resolution, whether there is a big difference in the data that you have from different parts of the world, and whether that affects how good high resolution modeling can be in different places.
So for weather forecasting, the answer is yes, because if you push your resolution, you also need to push the initial state that I was talking about, right? That needs to be at that resolution, and you need observations that support that. For climate, it's not so clear. The reason why this kilometer is such an obsession, right, is that the one process we know is super important for the climate system is called convection. That's these thunderstorms, right? And in the tropical latitudes, they are everywhere, all the time. There's lots of them. And not being able to represent, and they're kind of part of the heat engine of the system, right? They're kind of driving what's happening to the climate in a major way. And having to represent them by one of those parameterized models is it's not great. We had no choice, and we've done it. And I've actually worked on that for most of my career, and it's fun to work on. But there are limitations what you can do. And going to kilometers eliminates that altogether for the thunderstorms. That's where it's coming from. So it eliminates a major headache. Doesn't just make a little bit of a difference here and there, and we'll see what happens. It eliminates a major headache. That's why we are so keen on it. But it's not something where we're gonna do hundreds or thousands of years of simulations anytime soon at those resolutions. We're still learning. And maybe we can use those models intelligently to learn how to improve the coarser resolution models that we actually have to do these longer simulations. It's all a bit up in the air, but we are just at this really exciting point in time where it's become possible to do, at least a few years, maybe a few decades at these kilometer scale resolution and find out what happens. So it's at the moment, it's in the science realm, not in the prediction realm yet. So but it's very exciting.
Thank you.
Any more questions? Okay, I think that was it. All right. Well, thank you again, Christian, for that fantastic talk. I really enjoyed it. And also a great discussion afterwards. Thanks for answering all those questions.
No worries.
Please stay with us. So we have two posters now.